Welcome to another video lecture with me, Mr. Wolf. Today we're going to look at torque, and we're going to do that sample problem of a fireman on a ladder trying to fight a big burning building fire. What we're looking at here is net torque and net forces. Now torque is not a new force or anything. It's just a force that causes an object to twist. So it's a push or a pull. We can say look at torques as being caused by gravity or something pushing on it or other different forces. But it's something that twists an object about a rotation, about a center of rotation, a point of an axis. It is the units for a torque are a Newton meter. It's not a amount of energy. So torque is different than energy, but it's really the idea, and I keep repeating myself, but it's the idea to get an object to twist around a point of axis. I'm saying that wrong. I should be probably saying it differently, but right now as I'm doing this, I don't know the better way to do that. So I apologize. Here we have our fireman on the ladder. We have the ladder has a weight, 355 newtons. Ladder length is 8 meters. We have the weight of the fireman, 875 newtons. He's at 6.3 meters. My first step, whenever you have a torque problem, this is we're going to go through how to solve these problems. My first step is going to be to draw a picture and label the forces. This is maybe fun, best step possibly, but we're going to just start here. So here's our ladder. I've decided to make this, the bottom point of the ladder, my center of my axis of rotation. So that way I don't need to worry about the torques on there. A little bit more about that in a second. But okay, first force I have is the weight of the ladder. The weight of the ladder is going to be at the center point of the ladder. So that's going to be halfway up, so I can say up. Here we have weight ladder. Maybe a little small, but that's the weight of the ladder right there. Next, a little further up, now 6.3 meters up, we're going to have the weight of the fireman. And he'll go red. So there's that. So there's the two downward forces, the weight of the ladder and the weight of the fireman. Now we also have a force that's going to be provided from the wall right here. So there's the ladder leaning against the wall. It's the normal force from the wall. And just to follow along with this example in the book, I'm going to label this force P. So far, I have weight of the ladder, weight of the fireman, and the force from the wall coming out on this arm, radial arm here, this ladder. Now, there's also going to be two forces on the ground here. There's going to be a normal force from the ground pushing back up, and there's also going to be a force of friction. If there was no friction, this ladder would just slide down. So the force of friction is going to be acting in this direction. So I'm going to label these in what color? I'm going to stick with black here. We'll go another way to look at these is the force of the ground in the y direction and the x direction. I labeled them as the force of friction going horizontally and the normal force going up. Now, we can look at this in a couple of different ways. First, I'm going to look at this as a free body diagram. We have all of our forces here. Let's sum up all the forces and figure out which forces are in the x and the y direction. Simple enough. Force of friction is in the x direction, and the pushing force from the wall, the normal force from the wall acting back out, is also in the x direction. So I'm going to say, and I'm just going to use x and y, this is positive, this is negative. So force of friction, and then a negative p. Now my net force in the x direction is 0, because the ladder is not accelerating in that direction. It's stationary. It's in what we call equilibrium. So equilibrium, acceleration is 0, net force is 0. Just from this, I can tell that the pushing force from the wall is equal to the force of friction. All right, that's one step done. Next, let's look at the y direction forces. I have the normal force from the ground acting up. And you know what? Because I have F net here, I'm just going to change this to be normal force N, just plain N. Sorry to go back and kind of change that around, but it's just going to be N for the normal force. So I have a positive normal force minus the weight of the ladder minus the weight of the fireman. So I have the weight of the fireman, weight of the ladder acting downward, and once again, this ladder is not accelerating in the y direction. It's in equilibrium, so the net force is 0. All right, so I have net force here, 0, net force. So the weight of the ladder plus the weight of the fireman is equal to the normal force acting up. We already know the weight of the ladder and the weight of the fireman. We can find this normal force. We can go through and find the different forces in here by using these free body diagrams and drawing and creating our axes and setting it up in this table. X and Y table, really helpful. Next, and this is the new part. Now I'm going to explain why I have this as my center of rotation. We're going to look at the torques. We know, as I've said before, that it's in equilibrium. This means that it's not actually rotating. The net torque, and hopefully you can see this down here, net torque is 0. Now, the reason I choose this as my axis of rotation is because these two forces being here applied at that point will provide no torque. Their distance, or from the axis of rotation, is 0, so the torque provided by them is 0. I'm going to write the formula for torque. So torque depends on the force and the angle that it acts on the radial arm, and then how far down the arm it actually is. So in this case, R is 0, so both of these are not going to apply torques on this ladder. So I don't need to worry about them. But let's look at the forces, the other forces acting on this ladder. The first one we come to is the weight of the ladder. It's going to apply a torque. It's applying a torque downward. And I'm just going to say, since it's going clockwise, I'm going to say it's a positive torque. I don't know why I decided to do it right now, but I'm going to say that in the clockwise direction, that's going to be a positive torque. Because if you think about it, I have two forces going that way, and then I have another force, or another torque, opposing it going the other way, trying to spin it back that way. We know that the net torque is 0, so all of these torques must cancel out. But let's go through and set up our table. So first I have the torque provided by the ladder. Torque, weight, ladder. Next, I have the torque from the weight of the fireman. Torque, weight, fireman. Finally, I have the torque of the pushing force from the wall. So that's the wall pushing back on the top of the ladder. So I have the torque of the wall, and this here is going to be negative because it's going in the opposite direction. All right, now how am I going to calculate all these out? Well, the weight of the ladder, the force, is equal to 355 newtons, so I'm just going to write that, weight, ladder. The angle it makes with the radial arm, if this is 50 degrees, this inside angle is 50 degrees, this angle right here is going to be 40 degrees. Same for up here, 40 degrees, 40 degrees. So, weight of the ladder, sine 40 degrees, times the radius, so how far down the ladder this was. The weight of the ladder is going to act halfway down the length, so that's going to be at, if the ladder is 8 meters long, this is going to be at 4 meters. Next, I have the torque provided by the fireman. So the weight of the fireman, that's the force, Let's do this in red. Let's make it organized. Weight of the fireman. Again, it's at that same angle. It's going to be 40 degrees. And our radial distance down the lever arm for the fireman, it's at 6.3 meters. Finally, my last torque provided, and this is going to be in the counterclockwise direction, so we're going to say this is negative. This here is provided by the pushing force on the wall, and I'm going to say this is P. Now the same, it's based on doing a little geometry here, we can say we know that the angle is 50 degrees. 50 degrees for that. And this force is going to act at the end of the ladder, so this is going to be at a radius of 8 meters. At this point, I can go through and I can solve for all the different things I don't know. The force of friction, the normal force, all of this stuff. I know that my net forces in the x and the y direction all add up to 0. And I know that the torques here all add up to 0 as well, because this is in equilibrium. So it's not rotating at all. There's no net acceleration. So I know that the torque of the ladder plus the torque of the firefighter is equal to the torque provided by the wall up here on the top. They're going to cancel out and add up to 0. Alright? So, what I want you to do, you need to go through and solve for this force of friction. And really what you need to do is go through and solve for the pushing force from the wall from the torque. This is that force right there. That's the one unknown that we don't have, that you don't know in this part right here. And we can go through and solve for that. Alright? So hopefully this was helpful in explaining the problem. Please come in and ask any questions during class, and have a great afternoon.